Dear IoT openers, welcome to the lecture on data and information management in the Internet of Things, where we will highlight the main issues and challenges of data management in the IoT context, coming up with a generic schema and a workflow for dealing with them. IoT is data-centric. Tens of billions of IoT devices produce zettabytes, that are 2 to 70, of data per day, corresponding to 10 to 21 or billion or trillion of bytes. Such data are mostly multimedia data and therefore unstructured. More specifically, 80% of the data generated by IoT are unstructured, while just 20% are structured, e.g. database or similar. Unstructured data growing 2 times faster than structured one. Another interesting statistics is that 19% of the world's data were created in the last 2 years. As shown by the figure, we already surpassed the yottabyte frontiers, that is 2 to 80 or 10 to 24, of data globally generated in 2015. And the target is now for brontobytes 2 to 90 or 10 to 27 by 2020, and geobytes 2 to 100 or 10 to 30 by 2025. This opened up several challenges in IoT data management. What are the main IoT data management requirements? Complex applications require multiple data sources that are further aggregated, fused, and processed all together. Complex, multi-structured data are usually modeled through specific data format, styles and tools such as JSON. Another challenge is business data agility, aiming to adapt and evolve the system to new operating conditions, requirements, and/or environments. These require flexible solutions for managing data, such as dynamic NoSQL database schema, able to support continuous innovation, continuous integration and delivery, monitoring and feedback from operation. Concept included under the big umbrella term of DevOps, from software engineering, development, operation. To deal with these multiple data, widely variable application, also ask for single view providing an all-encompassing uniform view of data, aiming at business process convergence. This implies to aggregate data from multiple source systems and to define single schema, update whenever the source systems change. Then, operational insights require real-time support for time-constrained and critical scenarios, as well as security, privacy, reliability, performance, and quality of services requirement. So, how to deal with all such issues in IoT data management? The best strategy is to split the problem into stages, thus obtaining an IoT data workflow and an IoT data lifecycle. The IoT data lifecycle is therefore quite complex and kinky. From a technological perspective, the main aspects to deal with in IoT data management are data source. Data generation and production is a relevant part of IoT, involving sensor, probing the physical system. Data collection and gathering. Once data are generated, this should be gathered and made available for processing. The collection process needs to ensure that data gathered are both defined and accurate so that subsequent decisions based on the findings are valid. Some types of data collection include census, data collection about everything in a group or statistical population, sample survey, collection method that includes only part of the total population, and administrative byproduct. Data collection is a byproduct of organization day-to-day operation. Usually, wireless communication technologies such as ZigBee, Bluetooth, LoRa, Wi-Fi, and 3 or 4G networks are used by IoT smart objects and things to deliver data to collection points. Filtering is a specific preprocessing activity usually performed at data source or data collectors, IoT, nodes, e.g. modes, base station, hotspots, gateways, aiming at cleaning noisy data, filtering noise and not useful information. Aggregation and fusion. In order to reduce bandwidth before sending data to processing nodes, these are further elaborated, compressed, aggregated, reducing the payload, and fused, sensor data fusion for improving the quality of measurements, to reduce the overall volume of raw data to be transmitted and stored and improving the data quality. Processing. Once data are properly collected, filtered, aggregated, and fused, they can be processed. Processing can be both local and remote, and usually also include pre-processing activities, aiming at preparing data for real processing. Local processing, when possible, is mainly tasked at fast, lightweight computation on edges, edge computing, quickly providing results and local analytics. More complex computation are usually demanded to remote physical or virtual servers, either provided by local nodes, e.g. communication server or cloudlets, in a fog computing fashion, or by cloud providers as virtual machine hosted in data centers. This kind of computation can also involve historical data, providing global analytics, but hardly meets time-constrained application and real-time requirements. Storage, update, and archive. Remote servers are also used for permanently store and archive data, making these available for further processing, even to third parties. The database is often used for that, mainly based on distributed NoSQL key store technologies to improve reliability and performance. Delivering presentation visualization. The result of processing activities have to be then delivered to requesters, end user. These have to be therefore properly organized and formatted, ready for end users. IoT data visualization is becoming an integral part of IoT. Data visualization provides a way to display this avalanche of collected data in meaningful ways that clearly present insights that are hidden within this mass amount of information. This way, 3 patterns data path can be identified in the IoT data lifecycle: real-time live on edge, near real-time on edge fog, offline on fog cloud. The flow of data may take one of these 3 paths. Real-time, it is the loop on the left, for autonomous system within the IoT that proceed from query to production to in-network processing and then delivery. Near real-time, that is the outer loop, that starts from production and proceeds to collection and filtering, aggregation, fusion, and ends with data delivery to initiating possibly global or near real-time queries. Online processing, that is the inner loop, path that extends the production to aggregation further and includes preprocessing, permanent data storage and archival, and in-depth processing and analysis.